So this is example number 4 on helical compressive springs under fatigue. What we are trying to design here is a service valve spring that is actually that's manufactured from Unpin ASTM 232. And we want to use some standard sizes. And we know that it goes from 10 to 30 cycles between that is preloaded to 10. So your problem basically saying is I have a spring. I got my spring, and your spring has a preloaded value. It's preloaded to 5 pounds. And then it fluctuates between 10 and 30. Okay, so it's going to fluctuate between 10 and 30. And so if I plot this, this is completely a 0. This is your preload, and is fluctuating between these two values. This is where it's actually fluctuating. Okay, and the clearance here is, that clearance is delta is equal to 0.45 inches. And we want to find, but we are told we have an additional factor of 1.5. So that means that I have my 1.5 multiplied by 1.2, that gives you 1.8. That's a new design factor I'll use. We don't add these up. We don't add them up. We don't replace this with the old 1.2. This is a standard value. We have to add that to our standard that was given. Okay, so the problem tells me that C is equal to 10. My D is equal to, is what I'm looking for, and my life cycle expectancies, that's what I'm looking for. I'm looking for these two guys here. Okay, so just to start the problem, I'm going to start with the initial guess. We need some material properties before we do anything. And what we could do, the first thing we do is we need to find the material. Okay, so we need to find what your SUT is. A times A d to the minus m. So if I go to the tables here, the material is, you can see here the material is A232, A332. So this is the exponent, and this is the value of A. Okay, so those are the values I'm going to use in my analysis. So that's why this is 169 d to the minus 1.68. And then this comes from, again, table 10.6, 0.45 SUT. This is 76.05 d to the minus 0.168. You have your G. Your G is 11.2 times 10 to the 6 psi. And since also your C is equal to 10, you can find your shear factor, and that gives you 4C plus 2. 4C minus 3 is equal to 1.14. And note that if your C becomes very, very, very small, it becomes less than or equal to 1, this whole thing, your stress becomes, your stresses become higher. And the reason behind they become higher is because stress concentration increases at the coils. That's what your a small spring index is not acceptable either. Okay, so the next thing we want to do in the problem is, as we move on, we want to modify your loads. Okay, so your F max is 1.8 times 30. That's given in the problem. That's 54 pounds. F max, F minimum will be 1.810. That will be 18 pounds. And then you have your uh, preload. Your preload in the problem was 5, and that gives you 9 pounds. Okay? So to start with my initial guess, that's what I want to do, because brings me closer to my what guess. I have so many possibilities from the table that I could possibly use. I want it to at least bring me closer to my first guess. To do that, we know that this equation is actually given by sigma yields shear yield and tau maximum, okay, for the maximum possible load. So this is 76.05 d to the minus 168. You divide the whole thing by kb, 8f max c pi d squared. I need to divide this by 100 because this is in KSI. This also has to be in KSI. Bigger or equal than 1. Don't forget this. You don't do this or you don't change this, you're going to end up yourself in big trouble. Okay, so I can solve for d, and you find that d has to be bigger than 0.1202. So if I do that, I go to my table, and what you find here in the table is for this particular value, I can start with this initial guess. Okay, so we did the analysis. I'm going to save some time here. When we do this analysis, we find that your factor of safety in short, and that's given the whole detail in your notes in the handouts is provided. Is less than 1, so it's not acceptable. So what I need to do is I need to keep on moving up. So I go to the another one up, and if I do that, you can again I ran this many different iterations. You can show that your factor safety in fatigue is actually less than 1. So that was not acceptable either. So I kept on doing many iterations until I came to this value that seemed to work. So just to show you, I am going to stick with gauge number 7 for the rest of the analysis. And then if we need to reiterate, we'll reiterate moving forward. Okay, so let's start that with my next guess. That would be, I started with this one and moved my way up to be able to actually find a more closer guess. So the one another thing you could do is, instead of using F max, you could use F shut, but then you will have to do the whole analysis. Sometimes it's not even necessary. Okay, so the next thing I want to do in the problem is for that particular for D equal to 0.1770, I find this value. So this is SUT, this is SY, and find your spring mechanics. This is standard. You find your mean diameter, you find your delta F, and remember this is just your work dynamic deflection. It was deflecting between 0.45. So that's given, and then you can find this, and you can find all the values that you need here. Okay, so once I have all the information, I find the number of active coils, and I realized I run into trouble with this. Gives me 2.4. The next one near to the closest fourth, you could make the argument that I'm probably in the middle. I could go to 2.25. But even if I go on the next one up, you realize that still my spring is going to fail. It's not within the range, so I have to actually redesign. I will have to redesign my spring. So how do I redesign it now? What do I do? How do I go about this? Well, in this particular case, I can increase your D. D is not a problem. So that's what I'm going to do. I'm going to start with a new guess. So we show that this did not work. So I'm going to go the next one up. So let's go to gauge number 6, where it says D is equal to 0.1920. Okay, so this is going to be the diameter for my analysis now. So I keep on moving. So just remember, you have to do your static checks, but you also have to make sure that the mechanics of the spring are, correct. So when you do this, I'm going to save myself some time here using this new gauge diameter. These are my new values for my allowables, your spring, your mean spring diameter, and your active number of coils. Now you can see that you're within the range. Maybe I may want to would like to increase this higher up, but for this purpose of this example, we can stop. But in real life, try to stay, higher than 3. You may want to go maybe up to, 5, 6. 6 is a good number. Anywhere between 6 and 12, that's kind of nice. But then for just to move on this example, this is then using table 10.1. This gives you 5.5. Okay. Then I move on to my analysis, and now I'm going to start with all my checks. The very first check you do is your static check. Okay. You start with your preload, and you check your preload, which I will have expected, and it is acceptable. Okay. So I move on, and so I move on, and then your next value, you have to do the maximum working load. That's at 54, and you calculate this, and you can show this is also acceptable. So now we're going to check it at shut. What happens when I'm completely at shut? To do that, I need to find my LS. Remember, again, this is the same as Y total. This is a good external checker that you should get the same answer. So you do this, and I find this. Then with the Y shut, I can find my F shut. And with my F shut, I can find my uh, shear stress as shut. And that gives me 46.58. And this shows this is acceptable. There's one more thing I need to check. Make sure that my stability check is good. And I again, just remember why I'm using this. This comes table 10.2, and this is assuming that steel and ground ends. So this gives me 10.099. And these are way below this, so there's not going to buckle. So buckling will not be an issue in in this particular spring. So now we can move on, and we need to do, the next thing we need to do is check number 3 is static check for fatigue loads. Okay, and this check says when this is F max is equal to 54 pounds, F minimum is equal to 18 pounds. That would give you FA is equal to 18 pounds. F mean is equal to 36 pounds. And then from here, you can do all your calculations, and it's all detailed in your handout. You finally get a value of KSI. Sorry, this is ASM, tau M. This gives you 28, 29. And your ratio will be tau A, tau M minus tau I, and you get a value of 0.667. Okay, then you want to make sure that this is safe, so you calculate S max, SM plus SSA. That gives you 42.34 KSI. You can see this is way below your sigma yield in shear sigma yield, and less than 100 KSI. So I passed your static check. Your next item, now you want to do your spring expectancy diagram. To do this diagram, you you want to calculate all these values. We already found this. Find the ultimate strength, your yield strength. We already found this. So I need this value and I need this value for your SN diagram. That gives you 133. And then I need to go to the next table, and the problem said it was uh, uh, 232, and it was unpinned. So these are the values I will use for this particular uh, load life cycles. When I do that, that's why I'm using this 0.42, 0.40, 0.38, 0.42, 0.40, 0.38, and evaluate this, you get this. So now you can draw your your diagram. Your diagram is going to look something like this, where this is the value at 10 to the 3. Remember, you can plot if you wanted this value at 10 to the 0, just go and extend this line, and maybe at 10 to the 0, somewhere there, you can plot the other value that will be way up here, and you could do that, but that's not necessary. That value, that's if you were to plot that, that is SSUS, and I don't need that value for nothing. But this is what when we're plotting. This value is 94. This value is, we use basically the end values. This is about 85. So this is what your plot looks like, and I want to design for infinite life. Okay, so with that said, now I need to find what my SE would be. That's my next thing. SES would be, that's my next item. So I'm going to use method number 1. Okay, using method number 1, I find that K infinite, assuming that this is 1, SEW, this is equal to 45 KSI, and then your ES is equal to 0.5 SEW US divided by SUS minus 0.5 SWS. That gives you 26.49 KSI. And you want to ensure, what we want to do in the problem is ensure that this is going to be actually less than SES. We want infinite life. Okay. To do that, we go to next chart, and we do all your calculations here. With this value, you got the tau maximum. I will give you these values. I found this. I know my SE for your preload, and these values are plugged in here. I get the value of 28. And you can see that you get a value here for 26. So this actually does not satisfy, and it does not pass. So at this point, I'm going to have to redesign this spring to make sure that it does satisfy the value, because I would like to have an infinite spring. For that, I am going to skip many steps. What I'm going to do is I'm going to rerun the whole thing with the next gauge in your table here. So we show that this did not work. So we will go gauge number 5 and see if that is any good. And then we will check your answers. Okay. So if you do the whole redo, you will find the following values are, I did the whole, the mechanics are good, the static is good, everything is good. Just want to focus here on the new iteration for the strength check. And you can see that these are the new values, and this increases, but however, your endurance limit will also increase. So therefore, this is less than that, infinite life, so it passes. This is positive, which is acceptable. And then for the frequency check, both ends are in contact, keeping all the same. The only thing I'm changing is your D. Um, so by doing that, you can see that this is this is acceptable as well. Is within the range. Uh, just want to point out that this number also changes. This number now becomes uh, uh, 5.75 with the new load. So that's going to also be different. 3.75. So, and what you can see in the problem itself, everything else is, this is what you would give to the designer to complete this problem. Okay, so this is your final recommended spring design that will be valid for both static and fatigue. So this completes example number 4.